So this is Dr. Poe, and today I'm going to explain how to assign oxidation numbers. And this is really important because this will really help you in determining what is oxidized and what is reduced. And that is really challenging vocab, and you really have to pause and think about it. I know I always have to, and I've been doing this for years. And so just like pausing and thinking, that's going to help you a lot here. Okay, so just a couple, these are my super simple, not going to carry you through every single example you'll ever see ever, but will definitely get you through right now oxidation number rules. And one important one to remember is anything in the element state, the oxidation number is going to be 0, right? So what do I mean by the element state? So that would be if the atoms are identical in the compound, or if it's something that you see like legit off of the periodic table. So if the atoms of the compound are the same, oxidation number is 0. So like things like oxygen, hydrogen, iodine, bromine, chlorine, those exist in the element form as diatomic molecules. So if you see those, then you're going to know that all those atoms are the same. It's actually an element. Oxidation number is 0. Anything that you see that's legitimately off of the periodic table, go ahead and look through this list and see if there's anything that you just see that you know is a symbol from the periodic table. That oxidation number is going to be 0. So sodium, carbon, magnesium, iron. All those oxidation numbers are 0. When they get into compounds, when we see two different atoms bound together, that's when these oxidation numbers are going to be really, really helpful for us. Okay, and then there's a couple rules just to get us going. Generally, in most cases, the oxidation number of hydrogen in a compound is going to be +1. In most cases, oxygen in a compound is going to be -2. There's some exceptions to those, like for example HF. That can be +1, but we're not going to worry about that at this point. And there's plenty of other resources and other videos out on the internet that give you like really detailed examples, but I'm just covering the basics here. What do you need to get by? Okay. So if you see one of those, that could be a really great place to get started, especially in covalent compounds. In most cases, though, the oxidation number is going to be equal, especially in ionic compounds, it's going to be equal to the charge of the ion. And then something that's really important to remember as well is that all oxidation numbers of each atom have to add up to the overall charge. So that's going to help in polyatomic ions. In compounds, the overall charge is 0, and those are the examples I have. I'm just keeping it super simple, just as an introduction. You can go to more advanced examples after you've mastered the basics. Okay, so in terms of hydrogen and oxygen, those are really useful when it comes to covalent compounds like we see over here. Carbon monoxide, carbon dioxide. And so we can tell they're covalent. They're both of those atoms are nonmetals, and they have names that have those number prefixes. So what's the oxidation number of each of these atoms? Well, that's tough because carbon is in group 4. It doesn't really readily form ions. So what charge would we put there? Because I said that oxidation numbers and a lot of times are equal to the charge. So this is where that oxygen being -2, that's going to come into play. So if we start there, and we know that the overall charge is 0, because the compounds are neutral, and if there was a charge, it would be up here in the upper right-hand corner. So the question is, what plus -2 is going to give us 0 overall charge? And the answer is +2. So the oxidation number of carbon in carbon monoxide is +2, because +2 and -2 gives us the overall charge of 0. Okay? And so let's back it up and go to an example, an ionic example, because those are really straightforward. An oxidation number equals the charge type of example. And so if we see a metal and a nonmetal, we know those are ionic, and we just write down the charges. charge of sodium ion is +1. Charge of chloride ion is -1. +1 and -1 equals 0. We see that there's no overall charge here. If there was an overall charge, it'd be written right there. Same with magnesium oxide, MgO2 over here. Wait, MgO. I'm silly, because magnesium has a charge of +2, and oxygen has a charge of -2, and that still fits our -2 type of rule here. And +2 and -2, there's one of each. That's going to give us 0. Okay, so let's go into an example where there's multiple atoms. And so to really kind of emphasize this, what color do I want? Dark blue. This all oxidation numbers of each atom add up to the overall charge. So that was really easy so far when everything is just, we've just had examples with 1. But here in H2O, let's do an example where there's 2 H's. So following these rules, H is +1, and O is -2. If we added that up directly, then that would be an overall charge of -1, but we know that's not true. So that's when we consider how many there are. There are 2 H's, so there should be 2 +1 charges. So when we add up +1 and +1 and -2, we get an overall charge of 0. So the oxidation number of hydrogen in this compound is going to be +1. The oxidation number of oxygen in this compound is going to be -2. And that's because in our work shown up here, everything is adding up to 0 when you consider the number of atoms. So now let's go to CO2 for another example of that. Following our rules, oxygen is going to have a number of -2. There's 2 of them, so we have to write that -2 twice. And now our question is, what's the charge of carbon to make the overall charge 0? So -2 and -2 is -4. What -4 is 0? The answer there is +4. So here's a really interesting point. Carbon in carbon monoxide is +2. Carbon in carbon dioxide is +4. That's because carbons in these covalent compounds are a little tricky. So final answer here, carbon is going to be +4, oxygen is going to be -2, and that's because they both, adding up all of those across all the atoms gives us the overall charge of 0. And then something like HCl, that's really straightforward. Charge of H, generally +1. Charge of Cl, as is its charge, -1. So oxidation numbers generally equal to charges. If there's multiple atoms, remember to consider each atom is going to have its own contribution. So write out that number twice when you're showing your work. Okay, that's all really great, but let's go ahead and do an example bringing this all together. Rusting of iron. Okay, so I'm going to go ahead and balance this, and we're going to need 2 and 3 there, so that's 6 oxygens and 6 oxygens, and 4 irons on each side. Okay, so our steps to solve this are 1, assign oxidation numbers to each atom, because that could be a question. And then we're going to determine, I really don't like that sound, and I tried to turn it off in the settings, and I don't know how. We're going to determine what is oxidized, what is reduced. And then we're going to do the agents. What is the oxidizing agent? What is the reducing agent? Okay. So let's go ahead and get started. So you can pause and try to assign oxidation numbers to each atom in all of the above. And then we're going to determine oxidation number, reducing, what is oxidized, what is reduced. Remembering that those are always going to be on the reactant side, not the product side. So it's either going to be iron or O2. And then we're going to determine reducing agent, oxidizing agent, again from the reactant side. Okay, so iron is in the element state, oxygen's in the element state. Their oxidation numbers are 0 for each. So that's what we're doing right now. For Fe2, the charge of Fe2, is over here. It becomes the number of atoms of oxygen. So this was iron 3 oxide. And that 2 came from the oxygen. So those are our final answers for oxidation numbers. 0, 0, plus 3 minus 2. So now let's use this information to determine what is oxidized and what is, I want the red, not this circle thing, and what is reduced, because red has to be in red, obviously. Otherwise your notes won't even make sense. Okay, so what is oxidized and what is reduced? So we know what is oxidized is going to have an increase in oxidation number from reactants to products. So that which of these did the number go up? So if we look at iron, it went from 0 to plus 3. And if we look at oxygen, that went from 0 to minus 2. So one of those obviously went up. That was iron. So what is oxidized is iron, because that went from 0 to plus 3. So this was an increase of 3. Whereas what was reduced is oxygen, because we started at 0 and it got more negative. That number went way down. That we are in debt now, and that sucks. Okay, so what is reduced is oxygen. What is oxidized is iron. Okay, so the oxidizing agent is what caused the oxidation. Oxidation. Okay, so imagine oxidation is a crime. What caused the oxidation crime? So if your wallet is stolen, somebody did that to you. They caused that. So yes, your wallet was stolen, or your electrons were stolen. Something else did that to you. So that's what you have to think of when you're thinking about oxidizing agent. So what caused the iron to become oxidized? What caused its wallet to be stolen? Well, the only other thing in the room, the only other perp here is the oxygen. So the oxidizing agent caused the oxidation, and that is O2. What is reduced and what is the oxidizing agent are always the same thing. Always. It becomes reduced. It causes oxidation. Okay. And then similarly, what is oxidized is always the reducing agent. So this caused reduction. It became oxidized. So that's Fe. And honestly, if you just write it in this order, oxidation, reduction, then you are 100% set, and it doesn't even matter if you do agents first or whatever. The middle ones go together, the outer ones go together. So if it just doesn't make sense to you right now, you're going to have to think about it some more. Just set it up like this and you always get the right answer. Outer is the same, inner is the same. And just as like a side note, oxidation is what causes wrinkles, and we get wrinkles because of oxygen in the air. So if you're thinking of something that causes oxidation, a really good oxidizing agent is typically oxygen. If there's an option in the problem that oxygen could be the oxidizing agent, choose that, because it's most of the time true. There's just something more oxidizing than oxygen around. Okay, so I hope that was helpful, and so we can review really quickly. Oxidation numbers are not that scary. They're just generally the charge. If you have an ionic compound, it's just the charge. We can add up the individual oxidizing numbers of each of the atoms and when we add up all of those little charges, it should equal the overall charge. Generally, hydrogen's +1, oxygen's -2, and if it's an element, including those diatomic elements, like O2 and I2. Make sure that you're writing a 0 for their oxidation numbers, and then you will get the correct answer. There's plenty of other resources for this on the internet that go into more complicated examples, but this is a fantastic start. Thank you for your attention.